Okay, so we're moving on to 5.2, which is all about differential rate laws and determining differential rate laws. So this problem is already done for you, where we've found the order with respect to both carbon monoxide and nitrogen trioxide. We've found the overall reaction order by adding up the two orders, and we've written a rate law and determined the value of K. So we are going to work through the rest of these together. So this first one says we're going to consider this reaction where this is a decomposition reaction. Our rate law says that it is bimolecular decomposition reaction. So it asks us, it gives us a concentration and it gives us a rate, and it asks us to find K. So we're just going to substitute in. We know that the rate equals K times the concentration of NOCl squared. So we're going to plug in this rate. So we have 9.32 times 10 to the negative third molar per second is equal to K times the concentration of NOCl, which we know is 0.391, and that's moles per liter, or molar, and we're going to square that. And so we have, once we have a calculator, here we go, 0.391 squared is 0.1553 molar squared times K equals 9.32 times 10 to the negative third molar per second. Now we're going to divide both sides by the 0.153. And we're going to get that K equals 0.0610 because it's 0.096, so we have to round that up. Okay, so we had molar divided by molar squared, and so we're going to have 1 over molar times seconds, and that's our value for K. And then it says, what will the rate of reaction be when the concentration of NOCl is 0.634 molar if the reaction takes place at the same temperature? The fact that the reaction takes place at the same temperature tells us that K will be the same. And so now we're solving for rate, where rate equals K, which is 0.06101 over molar times seconds, times, and our new concentration, 0.634 molar squared, and we are again just plugging in and substituting. And we get that our new rate is 0.0245 molar per second. Or we could write this as 2.45 times 10 to the negative second molar per second. Okay, so that's how we solve that problem. Now let's flip over, and we're given this law. We're told that it is equal to K times A to the 0, B to the second power. Overall reaction order is just the order with respect to A plus the order with respect to B. So we have 0 plus 2. Our overall reaction order is 2. And then it gives us concentrations and a rate and asks us to solve for K. So once again, we're just substituting into the equation. 8.31 times 10 to the negative second molar per second equals K times 0.023 to the 0, which we know is going to be just 1, times 0.054 molar squared. This is also molar. Sorry, but that's raised to the 0. And so we have K is equal to and we get that K is 28. 28. 1 over molar times second. Only 2 sig figs, so the answer only had 2 sig figs. So now we get to actually work through one of these experiments. So the first thing we're going to do is look for, if I'm trying to find the order of reaction with respect to x, I want to find a set of experiments where x is changing and y is staying constant. So I'm not going to choose 1 and 2 because in that both x and y are changing. So I'm going to compare experiment 1 and experiment 3 because then y is staying the same and x is changing. And so I know that the 3.0 times 10 to the negative 4th over 3.0 times 10 to the negative 4th is equal to 1 over 0.5 raised to some power. An x, since I'm already working with x, I'm going to call this a. So I have 1 is equal to 2 to the a, and so I know that a must equal 0. So I know that it's 0 order with respect to x. And now I'm looking for one in y, where y is changing and x is not. So I'm going to pick reactions 2 and 3, because y is changing, but x is not. And so, because this number is bigger, I'm going to put this number on top. I'm going to have 0.70 over 0.35 raised to some power equals 1.2 times 10 to the negative 3rd over 3.0 times 10 to the negative 4th. And that gives me that 4 equals 2 to the b, and b therefore must be 2. So I know that it's second order with respect to y. So my overall rate law is that rate equals k times x raised to the 0 times y raised to the second power, or we could write this as rate equals k times y squared. It's okay to include this. It's also okay to leave it out. And then it asked me to use the experiment 1 data to calculate the value for k. Now we're just plugging into this rate law. So I have 3 times 10 to the negative 4th molar per second equals k times 0.35 molar squared. Alright, so I have 3 times 10 to the negative 4th divided by 0.35 squared, and I get that k equals 2.4 times 10 to the negative 3rd 1 over molar times seconds. And that's how we calculate that one. All right. If we have this reaction, nitrogen dioxide and hydrogen forms ammonia and water with this rate law, K equals nitrogen dioxide times hydrogen squared. If it is first studied with 2 molar for each of the reactants, by what factor will the rate change if concentrations are changed to 4 molar for both the reactants? So if I'm doubling both of these reactants from 2 molar to 4 molar, then that means that I'm effectively putting a 2 inside here, 2NO2, and a 2 inside here. But this 2 is being squared, and so I have 2 times 2 times 2, so it's going to change by a factor of 8. So it's going to be 8 times faster. And then number 4, again we have a reaction of oxygen with nitrogen monoxide to form nitrogen dioxide, and we have a termolecular reaction, so we have all three are colliding to create this rate law. If I double the concentration of oxygen, because oxygen is squared in the rate law, it's going to be 4 times faster because that 2 has to be squared. Okay. Now, again, we're looking for a differential rate law, and we're given experimental data, and we're asked to find the order of reaction with respect to dichromate. So we're going to find something where dichromate is changing and the others are not. So if we look at this reaction right here, we can see that the nitrous acid and the hydrogen ion concentration are constant, but the chromate ion concentration is doubling. So we have 0.50 over 0.25 raised to some power is equal to 8.4 times 10 to the negative third divided by 2.1 times 10 to the negative third. So I have 2 x equals 4, and so x equals 2, so it's second order with respect to dichromate. Now, when we look at a case where nitrous acid concentration is changing, but the others are not, let's see if we can find one like that. 0.25. Okay, so if we look at this reaction, then the nitrous acid is doubling, the dichromate is staying the same, and the hydrogen ion is staying the same. So we have 0.48 over 0.24 raised to some power equals 2.1 times 10 to the negative third over 2.1 times 10 to the negative third. So we have 2 to the y equals 1, so y must be 0. So it's 0 order with respect to nitrous acid. Last one, hydrogen ion. Let's see. So here, this one is staying the same. This one is staying the same, but the hydrogen ion is tripling. So we have 0.30 over 0.10 raised to some power is equal to 6.3 times 10 to the negative third over 2.1 times 10 to the negative third, and so we have 3 to the z equals 3, so z must be 1. So it's first order with respect to hydrogen ion. So our overall rate law then is that rate equals dichromate ion concentration squared times hydrogen ion concentration. And now, oops, I forgot the K. In order to calculate K, we're simply going to pick a line and plug it in here. So we have 2.1 times 10 to the negative third is equal to molar per second is equal to K times 0.25 molar squared times 0.10 molar. And we're going to get that K is equal to 0.336. Now we have molar divided by molar squared gives us 1 over molar times second, but is also divided by molar again, so it's 1 over molar squared times seconds. Okay, so working through, we have more of these. We keep on practicing this concept. So we have here an example where A is tripling, B is staying the same, and nothing is happening to the rate, right? So 3 to the x equals 1, so it's 0 order with respect to A, because 3 to the 0 is 1. If we go back and do the math there, 0.045 over 0.015 raised to the x equals 3.1 times 10 to the negative third over 3.1 times 10 to the negative third. 3 to the x equals 1, and that's how we get the 0. Okay, so that's our reaction order for A. We can tell this because when we triple A, the rate doesn't change. Reaction order for B. So for B, now this gets a little tricky because we do not have a place where A stays constant and B changes. So we're going to have to use this one and this one. But the math is made a lot easier for us because this A is being raised to the 0 power, right? And so what we wind up with is that the rate here, 6.2 times 10 to the negative third over 3.1 times 10 to the negative third is equal to 0.30 over 0.030 over 0.015 raised to the 0 times 0.48 over 0.24 raised to the unknown power. Okay, and so we have 2 equals 2 to the y equals 1. This is first order with respect to B. And our value for K, so our rate equals K times B to the first, and so we have 3.1 times 10 to the negative third molar per second equals K times 0.24 molar, and so we get that K equals 1.3 times 10 to the negative second. Can't write and talk at the same time. 1 over seconds. And the overall rate law is rate equals K times B. And that's how we solve that problem. As always, if you have questions, let me know.